deep beneath the crashing waves of the Pacific Northwest, nearly 300 miles off the coast of Oregon. A silent and incredibly powerful transformation is taking place. While the world's attention is often captured by the visible peaks of the Cascade Range, like Mount St. Helens or Mount Hood, there is a monstrous geological engine working on the seafloor that arguably puts them all to shame. This is the Axial Seamount, the most active submarine volcano in the Northeast Pacific Ocean. And right now it is doing something that has scientists gripping their chairs in anticipation. The entire ocean floor in this region is moving. It isn't just shifting or vibrating, it is literally being pushed upwards by a massive influx of molten rock from deep within the Earth's mantle. The seafloor is inflating like a giant rocky balloon, and the rate of this expansion is raising a haunting question in the scientific community. Are we witnessing the prelude to a monumental transformation, or could this volcano one day replicate the legendary collapse of Mount Mazama, the ancient peak that created the famous crater lake? To truly grasp the scale of what is happening at Axial Seamount, you have to visualize the sheer isolation and pressure of the deep ocean. At nearly 1,500 meters below the surface, the weight of the water above is crushing. Yet the force of the magma rising from below is so immense that it is overcoming that weight, lifting the solid crust of the Earth by several centimeters every single year. This isn't a theory or a guess based on distant echoes. Thanks to the Ocean Observatory's initiative, or OI, Axial Seamount is wired up like a patient in an intensive care unit. It is the most instrumented volcano on the planet. High-speed fiber optic cables run across the seafloor, connected to sensors that measure every tilt, every tremor, and every tiny change in the height of the caldera floor in real time. And right now, those sensors are screaming. The caldera of Axial Seamount is a massive depression at the summit of the volcano, roughly the size of a large city. It's here that the most dramatic action occurs. Since its last major eruption in 2015, the magma chamber beneath this caldera has been recharging at a pace that is frankly startling. Scientists have noticed a direct correlation between the height of the seafloor and the timing of eruptions. In 1998, 2011, and 2015, the volcano erupted almost exactly when the seafloor reached a specific threshold of inflation. It's like a cosmic pressure valve. Every time the pressure builds to a certain level, the crust fails and the lava flows. But this time around, things feel a little different. The inflation is continuing, and the geological community is watching to see if the volcano will follow its usual script or if it's preparing for something much larger and more unpredictable. When we talk about Mount Mazama, we are talking about one of the most significant volcanic events in the history of the Western Hemisphere. Thousands of years ago, Mazama was a towering stratovolcano, much like the peaks we see today in the Cascades. But during a massive climactic eruption, so much magma was pumped out of the reservoir below that the mountain literally lost its foundation. The peak didn't just blow its top, it fell into itself, collapsing to create the sapphire blue wonder we know as Crater Lake. The comparison to Axial Seamount might seem bold. After all, Axial is underwater, and Mazama was a towering mountain, but the underlying physics of a caldera collapse remain hauntingly similar. If the magma chamber at Axial continues to grow and expand without a significant release, the structural integrity of the entire seamount could be at stake. The story of Axial Seamount is also a story of the Juan de Fuca Ridge. This is a divergent plate boundary, a place where the Earth is literally pulling itself apart. As the North American plate and the Juan de Fuca plate move away from each other, hot magma rises to fill the gap. Axial sits right on top of this rift. But it's also fueled by something even more potent, a hotspot. This is the same kind of geological feature that created the Hawaiian Islands. It's a plume of intense heat rising from deep in the Earth. When you combine a spreading ridge with a volcanic hotspot, you get a recipe for extreme activity. That's why Axial is so much more active than the surrounding seafloor. It's the focal point of incredible subterranean energy. Imagine the sensors on the seafloor as a network of microphones. Scientists use these to listen to the volcano. They hear the cracking of the crust as the magma pushes through. They hear the tiny earthquakes that signal the rock is reaching its breaking point. These aren't the kind of earthquakes that would knock over a building on land, but in the silence of the deep ocean, they are deafening indicators of unrest. By tracking the location of these quakes, researchers can actually map the movement of the magma as it migrates from the deeper reservoir into the shallow chamber right beneath the caldera. It's like watching the veins of a giant fill with blood. The question of rolling like a Mazama refers to the catastrophic nature of a caldera-forming event. In a typical axial eruption, the magma simply spills out through fissures, creating new layers of basalt on the seafloor. It's a relatively orderly process. But if the magma chamber grows too large, or if the internal pressure becomes too great for the roof of the chamber to hold, you get a collapse. In the massive underwater environment, a collapse of the caldera floor could trigger massive displacements of water. We are talking about the potential for tsunamis, though because this is so far offshore, the mechanics would be quite different from a coastal earthquake. However, the sheer energy involved in a caldera collapse is hard to overstate. It is the ultimate expression of volcanic power. One of the reasons scientists are so alarmed, or at least highly alert about axial right now, is that the inflation has reached levels that traditionally preceded the previous eruptions. We are in the danger zone. Why hasn't it erupted yet? That's what everyone is trying to figure out. Is the crust stronger than we thought? Or is the magma chamber deeper and larger than previous models suggested? If the chamber is significantly larger, it means it can hold much more energy before it finally gives way. And a larger accumulation of energy usually leads to a larger eventual event. Let's talk about the life that exists around axial, because it's just as fascinating as the geology. When these eruptions happen, they don't just create new rock, they create new opportunities for life. Hydrothermal vents, which look like black chimneys spewing toxic, mineral-rich water, are the lifeblood of this ecosystem. They are powered by the heat of the magma chamber. Giant tube worms, ghost white crabs, and swarms of specialized bacteria thrive in this environment, completely independent of sunlight. An eruption can wipe out an entire vent community in an instant, burying it under a fresh flow of lava. But within years, new vents open up, and life returns, colonizing the fresh rock in a beautiful cycle of renewal. If axial were to undergo a Mazama-style collapse, this entire ecosystem would be transformed on a scale never before witnessed by human scientists. The data coming from the OOI cabled array is truly a game changer. In the past, scientists would have to sail a ship out to the site once a year, drop instruments, and hope they worked. Now, they have a literal high-speed internet connection to the volcano. They can see the floor of the ocean rising in millimeter increments from their offices in Seattle or Corvallis. This level of monitoring has allowed them to predict the 2015 eruption with incredible accuracy. But the predictability of a volcano is always a fragile thing. Nature rarely follows a perfect schedule. The current delay in the expected eruption cycle is forcing researchers to reevaluate their understanding of how magma is stored and transported at mid-ocean ridges. Is it possible that axial is growing into something much more formidable? Some geologists suggest that the plumbing system of the volcano is becoming more efficient. Over time, as more magma moves through the crust, it creates permanent pathways that allow for faster and larger injections of molten rock. If the supply of magma from the hotspot increases, axial could transition from a frequently erupting, leaky volcano into one that stores massive amounts of energy for a singular, massive event. This is where the Mazama comparison becomes really interesting. Mazama didn't become a caldera-forming monster overnight. It was the result of a long-term buildup of a massive, silica-rich magma body that eventually became too buoyant and under too much pressure to be contained. But wait, there's a catch. Most submarine volcanoes like axial erupt basaltic lava, which is very fluid. This type of lava doesn't usually cause the massive, explosive eruptions seen at volcanoes like Mazama or Mount St. Helens. However, if the magma sits in a chamber for a long time, it can undergo a process called fractional crystallization, leaving the remaining magma richer in silica and gases. Silica-rich magma is much more viscous and much more explosive. If axial's magma is spending more time in the chamber due to this delay in eruption, it could be evolving. This hasn't been widely observed at seafloor spreading centers, but in the world of geology, the never-before-seen is always just one discovery away. The physical sensation of the seafloor rising is something that would be terrifying if you were standing there. Scientists use bottom pressure recorders to measure this. These devices are so sensitive, they can detect the weight of the water above them changing as the ground moves up and down. Imagine the crust of the Earth, several kilometers thick, flexing upward under the strain of millions of cubic meters of molten rock. It's a testament to the incredible forces at play. This isn't just a local phenomenon. Either. The activity at Axial reflects the health and movement of the entire Juan de Fuca plate. By practicing on Axial, where no one lives, we are refining the tools that will one day save lives on land. It's a natural laboratory of the highest order. Another intriguing aspect of the current inflation is what researchers call seafloor geodetics. By using GPS-like sensors on the seafloor, they can track horizontal movement as well as vertical. Axial is actually getting wider as it gets taller. The magma is wedging the plates apart. This gives us a front-row seat to the birth of new ocean floor. At most ridges, this happens in fits and starts over thousands of years. At Axial, it's happening so fast we can measure it in weeks and months. This rapid seafloor spreading is a vital piece of the puzzle for understanding how our planet resurfaces itself. What if the Mazama-style collapse is a bit of an exaggeration for Axial? Even if it doesn't fall into itself in one giant roll, a significant collapse of just one part of the caldera could still be a world-class geological event. Large-scale submarine landslides are a major concern. When a volcano grows too tall and unstable, its flanks can collapse, sending cubic kilometers of debris racing across the abyssal plain. These landslides can generate localized tsunamis that are incredibly powerful. While the Pacific Northwest coast is relatively far away, the energy from a massive flank collapse could still reach the shore. Scientists are also looking at the gas emissions. Just like a pressure cooker, a volcano needs to vent steam and gases. Researchers have found increasing levels of carbon dioxide. Gas-rich magma is arriving from the deep mantle. It's like the volcano is burping before a big meal. The chemistry of these vents is a direct window into the heart of the magma chamber. By analyzing the fluids, scientists can tell the temperature and pressure of the magma miles below the surface. Currently, those temperatures appear to be rising. The sheer volume of the magma chamber at Axial is estimated to be several dozen cubic kilometers. That is a lot of molten rock sitting just a few kilometers below the seafloor. If you think of the crust as a thin eggshell, you can start to see why the inflation is so concerning. The pressure from below is constant, while the strength of the crust is limited. At some point, the eggshell has to crack. The question is whether it cracks in 1,000 tiny places, leading to a gentle eruption, or if it cracks in one giant ring, leading to a Mazama-style collapse. One of the most exciting tools used recently is the Autonomous Underwater Vehicle, or AUV. These are robot submarines that can fly just meters above the seafloor, creating maps with centimeter-level precision. By comparing maps from before and after an eruption, scientists can see exactly where the lava went and how much the ground moved. They've discovered lava lakes and rivers of fire that exist for short periods on the seafloor. These maps show that Axial is a much more complex system than just a simple hole in the ground. It's a sprawling city of volcanic features, each with its own story to tell. As the inflation continues, the tension among the researchers grows. They are in a race against time to gather as much data as possible before the next event. Every ship that heads out to Axial is loaded with equipment to measure the water column, the seafloor, and the subsurface. They are looking for precursor events that could give us a few days or even weeks of warning. So far, the best warning sign has been the rapid increase in small earthquakes. When the quake rate jumps from 10 a day to hundreds an hour, they know the end is near. But what if the end is actually the beginning of something much larger? If Axial is indeed transitioning to a new phase of its life, we might be looking at the birth of a new kind of volcanic feature in the Northeast Pacific. The history of geology is full of surprises. We used to think that the seafloor was a slow, boring place. Axial seamount has proven us wrong. Violent and beautiful change. Whether it rolls like a Mazama or continues its steady rhythm of inflation and eruption, it remains one of the most important places on Earth for scientific discovery. Think about the sheer courage it takes to study a place like this. You are dealing with sensors that are sitting on a volcano that you know is going to blow. There have been times when lava has actually flowed over the cables, melting them and cutting off the data. But in those final moments before the sensors fail, they provide information that is priceless. They show us the temperature of the lava as it touches the water, the shock waves of the explosions, and the incredible speed at which the ground settles after the magma is released. It's a high-stakes game of observation. The Pacific Northwest is a region defined by its geology. From the mountains to the rugged coastline, everything we see is a product of tectonic forces. Axial seamount is the offshore cousin of this landscape, unrefined version of the processes that built the land we live on. By watching Axial, we are watching the Earth in its most creative and destructive states. The inflation we are seeing now is a reminder that the Earth is not a finished product. It is a work in progress. And Axial is one of its most active workshops. As we look toward the future, the goal is to create even more sophisticated models. We want to be able to simulate the entire magma chamber in 3 dimensions, predicting exactly where the next fissure will open. This will help us understand the risk of a caldera collapse and allow us to better predict the impact on the ocean environment. The more we learn about Axial, the more we realize how little we know about the 70% of our planet that is covered by water. There could be dozens of axials out there, growing and inflating in the dark, waiting to be discovered. The current situation at Axial is a prime example of real-time science. It isn't about looking at rocks that are millions of years old. It's about looking at data that was recorded 5 minutes ago. This immediacy brings a sense of excitement and urgency to the field that is hard to find anywhere else. Every time a new data packet arrives from the seafloor, it could be the one that signals the start of the next big eruption. And for a geologist, that is the ultimate thrill. Could a Mazama-style event happen in our lifetime at Axial? The odds are low, but in geology, low odds just means it hasn't happened recently. The capacity for the Earth to surprise us is limitless. What we do know is that something big is brewing. The seafloor is pushing up, the earthquakes are ticking, and the magma is rising. Whether it's a standard eruption or a geological game-changer, Axial seamount is about to teach us something new about how our planet works. For the people who live along the Oregon and Washington coasts, Axial is a distant but important neighbor. It's a source of wonder and a reminder of the power of the natural world. It reminds us that we live in a dynamic environment where the ground beneath our feet, even the ground deep under the sea, is never truly still. The silent giant off the coast is speaking, and thanks to modern science, we are finally learning how to listen. The next time you look out at the Pacific Ocean, remember that way out there, beyond the horizon, the Earth is literally expanding. Millions of tons of molten rock are forcing their way toward the surface, reshaping the world in total darkness. It is a spectacular show that has been going on for eons, and we are the first generation of humans, with the tools to see it happening in real time. The inflation of axial seamount is more than just a scientific curiosity. It is a pulse check on the planet itself. As the inflation continues to climb past the previous limits, the scientific community remains on edge. Is the volcano preparing for a massive reset of its system, or is it simply expanding its horizons? The ambiguity is part of the fascination. We are watching a giant wake up, and we don't yet know if it's going to stretch its limbs or tear down the house. But one thing is for certain: the data we gather from this event will change our understanding of submarine volcanoes forever. This is the beauty of discovery. We start with a question. We gather data and we find ourselves standing in front of a mystery even larger than the one we started with. Axial seamount is that mystery. It is a laboratory, a powerhouse, and a potential harbinger of change. It is the meat of the geological world, providing all the nutrients and energy that drive our understanding of the Earth's crust. And as the seafloor continues to rise, we can only watch and wait, ready to witness the next great chapter in the history of our planet. The technical achievements involved in this monitoring cannot be overstated. We have successfully wired a volcano in an environment as hostile as the surface of many planets. The high pressure, the corrosive salt water, and the distance from land make the OOI project a triumph of engineering. This infrastructure is what allows us to even ask these questions about Mazama-like collapses. Without it, Axial would just be a dark shape on a map. With it, it's a living entity. Researchers are particularly interested in the magma supply rate. This is the speed at which the chamber is being refilled. Recently, this rate has shown signs of increasing. A faster supply rate leads to more frequent eruptions, but it also creates more instability. It's like pouring water into a glass faster and faster. Eventually, the water doesn't just overflow, it splatters and breaks the surface tension in violent ways. Watching this refill rate is currently the top priority for seafloor geodesists. We also have to consider the role of the ocean itself. Does the weight of the tides affect when the volcano erupts? Some studies suggest that the small change in pressure from a high tide could be the straw that breaks the camel's back for an already stressed volcano. This shows just how finely balanced these systems are, from the gravity of the moon to the molten rock miles below the seafloor. In these quiet moments before an eruption, the caldera of Axial is an eerie place. Hot water shimmers above the vents, and the ground is littered with the glassy remains of previous flows. It's a landscape of fire and ice, perfectly preserved by the cold and pressure of the deep sea. But don't let the stillness fool you. The ground is rising, the tension is building, and the next great discovery is just beneath the surface. The comparison to Mount Mazama serves as a powerful reminder of what volcanoes are capable of. While Axial might not be a mountain in the sky, it is a mountain of the sea, and its power is just as real. Every centimeter of inflation is a promise of future action. Whether that action is a familiar flow of lava or a historic collapse remains to be seen, but the world of science is ready. We have the sensors, we have the satellites, and we have the curiosity to follow this story to its conclusion. As the Pacific Northwest prepares for its geological future, Axial Seamount will continue to be a focal point of study. It is our most direct link to the inner workings of the Earth. It tells us how the crust is made, how the plates move, and how life survives in the most extreme conditions. The alarm scientists feel isn't just about danger. It's about the excitement of witnessing a major geological transition. It's the thrill of the unknown. So, will it roll like a Mazama? Only time will tell. But as the seafloor continues to push upward, we are getting closer to the answer every single day. The giant is active, the ground is moving, and the ocean is holding its breath. We are privileged to be the ones watching this incredible story unfold. 1 millimeter of inflation at a time. The discovery of Axial's current state isn't just an update in a journal, it's a headline in the biography of our planet. Stay tuned as we keep our eyes on the deep Pacific. The story of the Axial Seamount is far from over, and the next update could be the biggest one yet. The Earth is speaking, and it has quite a tale to tell. We'll be here to listen, to analyze, and to share the wonders of our dynamic planet with you. The fire below the waves is rising, and the results will be nothing short of spectacular. Keep your curiosity alive and your eyes on the horizon. The most incredible discoveries are often the ones we've yet to see.